Okay, so now we're ready for the third part of our preliminary chapter, section P3, functions and graphs. And of course, there's a lot of other topics in this section too. We'll start with functions and functional notation. So, as I briefly mentioned earlier, a relation between two sets is a set of ordered pairs. But not every relation is a function. In order for it to be a function, as you recall, we discussed this in the last section, each x has to be associated with exactly one y. Um, if not, then the set of ordered pairs is a relation, but it is not a function. On the other hand, if each x is associated with exactly one y, then the set is both a relation and a function. Okay. You also remember that x is defined as the independent variable, y is the dependent variable on the traditional XY coordinate system. Okay, let me just quickly sketch that out for you. Not that anybody ever forgets the XY coordinate system, but don't forget that y is the dependent variable, x is independent. And what that really means is y is a function of x, not the other way around. Okay. And so again, as we've said in the last session, a relation is some set of ordered pairs. For example, so this is a relation. It's automatically a relation. Just the mere fact that we have a set of ordered pairs makes it a relation. But if you notice, x, which we'll list the x's here, we have a 1, a 2, and a 3. And here are the y's. What are they? 2, 5, and 7. And in this case, as you see, when x is 1, it is associated with y equals 2. X equals 2 is associated with y equals 5. And x equals 3 is associated with y equals 7. So this set of ordered pairs is relation and a function. Now, of course, most functions are expressed as an equation of some kind, but you always have the ability to express it as a set of ordered pairs if you want to. But obviously, it's more convenient to do this as a function, some kind of an equation that represents that function. Let's see. Oh, and now they're reminding us of the terminology here. For this function f of x, we'll call it the set of all possible x's that can be associated with this function. This is the domain, and this is the range. Although some books do call this the codomain, but I think this book always calls it the range, so we don't want to get confused. The domain is what, think of the domain. Let me just do this a little more informally. The domain of a function is the set of all x values that can be substituted into the function. And the range of a function is the set of all y values that result from substituting x values into the function. Or even more informally, you could say x represent the domain is what can go into a function, and the range is what can come out of a function. Okay. So I've actually seen a few books where they literally describe this as like a sausage grinder. You put meat in and sausage comes out. The meat that goes in is the domain, the range is the sausage that comes out of it. Okay. It seems like a little strange, but there it is. Evaluating. Okay. So evaluating a function. We actually did this already, but let's just go through this again. What does it mean to evaluate a function? Well, really, all you're doing is finding a specific value for y. Okay. Substituting. It means substituting a specific value for x. All right. So just as a quick example, if our function is, let's say y equals, um, I don't know, 3x squared plus 2x minus 4, and I need to know the value of the function when x equals 2, we often see it written in the following way. So what are we doing? We're replacing all the x's with a 2 and then solving. Okay, so now you can see for yourselves this is a parabola, and it just simply means that when x equals 2, y is 12. So let's say it looks something like this. Okay, now this is this is a hint as to what's coming up. You won't need this just yet, maybe in the beginning of chapter 1. This is a definition that will be coming our way later on in the course, and it's a very messy expression, as you can see. We'll get back to that later on. Um, so now here's where they're trying to show you that finding the domain and the range can be very challenging. So here's an example of that. Okay, now by the way, this part tells me that we're restricting the function to 4 or 5. Okay, so what exactly are we trying to find out? Well, here's the thing. Um, when we look for the domain of a function, the domain basically includes all real numbers such that substituting them into the function does not result in either division by zero or an imaginary number. Anything else goes, all right? So in other words, we're trying to avoid any situations where an x will lead. Now here you can see for yourselves, this is where we're going with this function. There's two values of x that would cause division by zero. Okay, well, let's see why. Okay, so in other words, x equals plus and minus 2, either one of those substituted into this expression will lead to division by 0. So that implies that the domain cannot include either 2 or negative 2. All real numbers except negative 2 and 2. Okay. Now, this can be expressed in a few different ways. If you look at Symbolab, the program we've been using to help us with the graphs, what they might do is write something like this. It's just a shorthand way of saying x could be anything except negative 2, positive 2. But often what we see instead is a more formal notation called interval notation, which is based on the idea that the real number line is an infinite set. And what they're saying to us here is that all of these real numbers count except negative 2 and positive 2. And on a graph like this, you would indicate that by a hollow circle. And then everything else is included in that interval. So you could sort of fill that in a little bit. So what we essentially have is three intervals. This is the interval from negative infinity up to, but not including negative 2. Everything from negative 2 to 2, not including either of the endpoints, and 2 up to infinity. All right, so let me just quickly review with you the notation that we use in these cases. If I have an interval, let's say something like this, I want to indicate that I'm including everything from 1 to 2, including both endpoints. I write it with square brackets. Okay. But at the other extreme, where I include neither, I have hollow circles and I use round brackets. All right. Oh, by the way, it does include everything in between. Let me just fill that part in. And then we have other cases where one endpoint is included but not the other. Okay, like for example, one but not two. So one is included because you can tell by the fact that it's a square bracket. Two is not included. It's a round bracket. And then, of course, the last possibility would be the other possibility would be not one, but two. All right, so I just want to remind you how this works so that when we use this notation, you won't be confused. I do want to point out too that whenever infinity is involved, infinity or negative infinity, we always use the round brackets. Okay. Now, the other thing I want to remind you about is some notation um, taken from set theory. This is the union operator, and it means you're combining two sets. Okay. So what's happening up here is that you've got three intervals that are being joined together. And so you would write this one in the following way. To indicate that I mean, it's a very complex way, I guess, in this case of showing that it's everything but negative and positive two. So, you might say, well, why don't we just write this? I think that WebAssign will insist that you use the interval notation. Okay, that's part of the reason, but you should be familiar with both of them. Okay. Now, we're going to go to Symbol Lab and see what this thing looks like so you can visualize why negative and positive two are not part of the domain. Okay, let's get that open. Whoops, hold on. 1 over, what's going on here? It's being very stubborn with me. Now that's probably not what you were expecting. Look at this. Now, it's hard to see there. Let me make it a little bigger. Those dashed green lines are where the function will never actually quite touch that line. You may recall from your travels that those lines that the function never quite touches are called asymptotes. Okay, so in other words, the function converges to an asymptote but never quite reaches it. So you can see here there's actually one horizontal asymptote, which is the x-axis itself, and two vertical asymptotes, plus or minus 2. Okay, so in other words, the function is discontinuous at those 2 points. You cannot have it actually ever equal negative, x cannot equal negative 2, and it cannot equal positive 2. It can get close, but it won't ever actually equal either one of those. So that means we have two vertical asymptotes, negative 2, positive 2. And this is true because we cannot allow x to either be negative or positive 2 because that would result in division by 0. Okay. Now, there's going to be a lot of discussion in the course about asymptotes. Um, you'll see as we go along, but it's good to remember that an asymptote occurs where there's a discontinuity in the function, often because that value of x would lead to division by 0. Okay. So that's what's happening here. Now, this one, imaginary numbers, let me just quickly throw an example out there. Oh, let's say if something like this. Actually, let's make it even simpler. Let's try this. Just x. So here it should be pretty clear that the x can never be negative. Why not? Because that would lead to a negative square root, which is an imaginary number, sometimes called a complex number. So therefore, in this case, the domain is all non-negative real numbers. Okay, and you would write it like this. Notice that zero is allowed because you can take the square root of zero. That's not a problem. But anything below that, negative 0.01 even, that leads to a negative square root, which we can't allow. Okay. So, by the way, I do want to also remind you of a little bit of notation. Actually, I should say terminology. Um, if x is always strictly greater than zero, x is positive. But if x is greater than or equal to zero, we change the name to non-negative. If x is strictly less than zero, we say that it is negative. And if x is less than or equal to zero, we say that x is non-positive. All right, so I just want to remind you what these terms actually mean. So here we have a domain of all the non-negative real numbers, meaning that positive or zero are allowed. All right. So here's one, just like the one we just did, the square root of x minus 1. We can do a quick graph right here. So you can see this time it starts at 1. We can have a 1 and anything above that, but we can't have anything less than that because that would result in a negative square root. Okay, so for that one, the domain, and you can see they're using this notation, everything from 1 up to infinity, including the 1. Okay. All right, let's only add that in here. All right. All right, so that's what they're explaining right here. How about this one? 4 minus x squared. Okay, so let's think about this. Why don't we do this? Why don't we set this equal to 0? So at exactly negative and positive 2, the function is equal to 0. Now, you notice that if x gets too large, we'll have a negative square root. So that means x can only go as high as low as negative 2 or as large as positive 2. So, Now that's a weird function. Okay. Um, oh, sorry. Wait a minute. What am I doing? That should be 0, comma 2. So this is what it ends up looking like. And the domain is everything between the 2 points. Oh, actually, no, sorry. It includes the two endpoints, so we need the square brackets. Wow. Look at that. Now that's a very interesting case. And yeah, here's their graph. Okay. Now, here's an interesting result. Um, there's different, even though we know how a function works, what does it mean to be a function? There are different special cases that we need to be familiar with. Okay. And among them, one of the more important ones is the notion of a one-to-one function. Okay. So a one-to-one function is a function that has an extra key property to it, which is this. So normally with a function, um, in order for a relation, we already know that it must be the case that for each x, there is exactly one y. Okay, now let me show you an example of this real fast. That might surprise you. Now, if you notice, this could be written as a set of ordered pairs 1, 2, 2, 4, and 3, 4. Now you might say, well, wait a minute, what's going on here? Both of these x's are associated with 4. That's okay. That does not affect the fact that it's a function because each x is associated with a single y. So this is still a function. And as a matter of fact, what we can do here is illustrate this with birthdays. Okay. So let's say instead of numbers, we have people and birthdays. Obviously, I have to do a very simple example of this. I'll just pick two birthdays. And let's say we have John, Bill, and Mary. John and Bill are twins. They were both born on January 1st, 02. Mary was born on February 3rd, 2004. So even though John and Bill have the same birthday, this is a function. Okay. Now, the one-to-one function has an extra requirement. Okay. So here it is. With a one-to-one function, each x is associated with exactly one y, and in turn, each y is associated with exactly one x. So in other words, it cuts both ways. And so this birthday function that I just showed you, well, it's a function, but it is not a one-to-one function because more than one person has the same birthday. Okay, so what would be an example of a one-to-one function then? Well, let me show you a generic example. Okay, so each x is associated with one y, but each y is associated with one x. So this is a one-to-one function. And how about a real world example? Okay, so this time instead of birthdays, I've got, well, these should look familiar. Now, of course, these are completely invented. Actually, I'll tell you what, let me see what I can do about making this a little neater. Well, these are obviously social security numbers. And these are obviously, well, we'll call them people, I guess, citizens, people. And naturally enough, even though John and Bill are twins, they can't have the same social security number. And so this time it is a one-to-one function. Their birthdays are not. Multiple people can have the same birthday, but nobody had better have the same social security number. Otherwise, there's going to be a problem. So this is a real world example of a one-to-one function. It's a little bit more restrictive, of course. In other words, not every function is one-to-one. Now, why does this matter? What is the big deal with one-to-one functions? Well, among other things, and this is something we'll get back into later on as well, a one-to-one function has an inverse. Oh, you might remember how that works. An inverse, um, let's say you have functions like, let me write it like this actually. F of x is x squared, and g of x is the square root of x. These are inverses because in effect they offset each other. Okay, so in other words, um, if I apply the first function and then the second function in either order, I'll wind up back with the original value of x. So therefore, they are inverses of each other. Okay. So if I have a function that's one to one, we know that it has an inverse. Now, onto simply means now, we haven't really been talking about the ranges so far. Remember, the ranges are the y's, okay? So a function is said to be onto if the range is all real numbers. Okay. Now, we're not going to get as much use out of that one as the one-to-one functions, but they want you to know this before they don't want you to forget this. Okay, great. Graphs. Okay, and here they're reminding us about the vertical line test. Here's some examples. The first one on the left is not a function because it fails the vertical line test. Actually, let me copy this into the notes so you can see it better. The one on the left, it fails the vertical line test. That line crosses the function twice. The middle one is a function. And believe it or not, the third one is a function too, because no matter where you put that line, it's not going to ever cross the function more than once. Now, here's an interesting twist. There is a test to see if a function is one-to-one. It is the horizontal line test. If a horizontal line crosses a graph more than once, then the function is not one-to-one. Okay, so let me show you a couple of examples. Okay, now y equals x squared is not one-to-one. It's a function, of course, but it's not one-to-one. In fact, if you were to draw out some values here, you'd see why pretty quickly. Okay, so you can see what's happening here. Um, Negative one squared and positive one squared both give us one. Zero, of course, squared is just zero. So while this is definitely a function, you can see that it's not one-to-one. Which means it does not have an inverse. On the other hand, here's a function that is one-to-one. No matter where I draw that horizontal line, it's never going to cross that curve more than once. Aha, so this one passes the horizontal line test. And therefore is a one-to-one function. All right. And that means it has an inverse. Okay. So let's see, what else do they want us to do? They would just like us to review a little bit what some of these standard functions look like. So the one on the far left, it's called the identity function because it crosses the axis, the origin rather, and it has a slope of 1. So that means no matter what point I choose, x and y are equal to each other at every point along here. That's why they call it identity. So the slope, whoops, it's not 1, it's x. Intercept is 0. This one is the square function. They call it squaring. It's the same thing. Cubic function, a polynomial like this with the highest exponent is 3 is called a cubic function. And this one is called, of course, a quadratic function. All right, so we've already kind of gone through this. And then in the next slide, we have a few more that we'll run into quite often. We've already seen the square root function. It starts at 0. You notice how it's only restricted to the first quadrant. Um, our old friend, the absolute value function. We haven't seen this in a while. You can see that you've got, if you remember how that works, it basically means that if x is positive, then the absolute value is that same number x. If x is negative, then you multiply that by -1. The bottom line is no matter what you do, y, that is, will always be positive. Now, here's an interesting one. This is sometimes called the reciprocal function, 1 over x. And you notice the domain does not include 0 because that would give us division by 0. So we end up with this. All right, well, that's not the best drawing I've ever done in my life, but you get the idea. And so you notice how the range, interestingly enough, is the same. In other words, x cannot be substituted into this function, but no matter what I plug in for x, the result will never be a 0. So that means both axes are asymptotes. Okay. What else do they have here? Transformations. Now, what they're talking about here is if you take a function like a quadratic function, you should be able to see the difference between two functions that are very similar to each other. So here, for example, the difference between y equals x squared and x squared plus 2, this is the intercept. So therefore, it shifts up by 2 units. This one is not so obvious. You'd think that adding a 2 here would shift it to the right, but it doesn't. It shifts it to the left. Okay, So by add, but you notice how this is included within the square. If not, then it's just a constant. So because it's inside the parentheses, adding 2 inside here moves the whole thing to the left. So this is 0, 0. This is -2, 0. So we can shift the function up, or we can shift it to the left or to the right. And if, they don't have it here, but this one would be y equals x minus 2 squared. Why does this matter? Because sometimes what will happen is you'll be working on a problem for a function that you understand very well, and you'll see that the results should be similar for another function that is only a little bit different. It might come in handy at some point. Okay. What else today? Oh, okay. So here, there's more transformations. So here they've changed the sign. We call this a reflection, by the way. Okay, this is x squared. This is negative x squared. They both start at the origin. This one, they've done two things. They've reflected it and they've, wow, added this to shift it to the left. And then this constant shifted it up by 1. And the negative, boy, they really went to town on this one. So the negative made it flip upside down. The +3 shifts it to the left, and this 1 shifts it up. And this one is a reflection. Okay. All right. I think that's enough of that. So now they're going to sort of remind us how to classify functions. We're going to see all of these as we go along. Algebraic functions include polynomial, radical, and rational functions. Trig functions, which you have maybe not thought about for a while, sine, cosine, tangent, all the rest of the basic trig functions. And then we have exponential and logarithmic functions that we need to look at. So the polynomial just means many numbers, but it has a specific format to be considered a polynomial. You can't just say, well, you know what, anything that has a bunch of x squares in it or something is a polynomial. No, it takes this form. This is said to be, sometimes it's called an nth degree or nth order polynomial. And this term is a constant, by the way. And so you can see that a cubic function, a quadratic function, they're both special cases um, of this. So we could say that a cubic function is a third degree polynomial. A quadratic function is a second degree polynomial. And a linear function is a first degree polynomial. But there are restrictions on it. Doesn't specifically mention that here. Oh, and a constant. I left that one out. A constant is a 0 degree or 0th is an adjective polynomial. Okay. Oh, there it is. I knew I overlooked it. Sorry. It was right there all along. The restriction here is that n, whatever n is, a non-negative integer, which means 0, 1, 2, 3, etc., etc. If it's not, let's say this leading n is 3.7 or something like that, then it's not a polynomial. It's something completely different. Okay. All right. Now we got that out of the way. And now it turns out that, as far as understanding the basic shapes of these graphs, the leading coefficient, as it's called, this is defined as the leading coefficient because it is associated with the largest exponent. Gives us some key information about the behavior of the function. Okay. So specifically, and they're writing it like this because it could be literally anything. It could be third, fourth, fifth, whatever. But they want us here to focus our attention on even degrees. If the leading coefficient is positive, then the function will fall and then rise. If it's negative, yes, you can see it'll rise and then fall in the following way. Okay. So, for example, I can show you quickly an example of the one on the right. That's what negative x squared looks like. Okay. And it has that same basic shape. I don't know any examples of this one on the left off the top of my head. Um, tell you what, we can look one up. Let's just go look on Symbolab for 4x squared, just to keep it simple. Oh, actually, no, that's just going to be a parabola. Let's try 4x to the fourth. That should be fun. No, you know what? That one's going to be not that interesting either. Um, I'm just randomly making one up now. You notice it has x to the fourth. It's an even degree polynomial. The coefficient is positive. Oh, yeah, it does have that kind of weird up and down shape. Good. All right. Now, these are for the odd ones, and that changes everything. And so the classic example of these I've shown you before. Um, and so, yeah, that's basically what they're trying to show you. Okay. Now, of course, the higher the degree of the polynomial, the more strange the shape will get. But this is the basic pattern that you'll see. Okay. Okay, what else do we have? Rational functions, the word tells us what it means. Rational means it's a ratio. That's all it is. It's a ratio of two polynomials. Okay. Some polynomial and rational functions are algebraic. Some of them, they're not giving us any examples of transcendental functions, but a function that is not algebraic is said to be transcendental. It has other very bizarre properties that I guess they'll save for another day. Um, oh no, they mention it right here that trig functions are transcendental. So, like, if you remember that the sine of x, it's like a big roller coaster. Oh my God. Well, all right, that's not great, but that would be defined as transcendental. It's clearly not a polynomial of any kind. Um, and then they're going to get involved here with algebraic operations on functions and composite functions. Now, that's a fairly complicated area of study. I don't want to rush through that. So I think maybe right about here is a good stopping point. Well, we're almost done with section 3 here, but there's a lot of very important content here. I don't want to rush through it. So we'll hang on to this until the next session. What is this, slide 41? And then we'll take it from there. And then, of course, there's a fourth part. And when that's done, we can finally get started with the new material. Okay. So I will see you all next time.